Hello everyone. In this video, we are going to learn the basic of Cascode Amplifier, and we are going to focus on computer emitter degenerated common emitter amplifier, because emitter degenerated common emitter amplifier is a part of the Cascode Amplifier. And now we just start with a pure common emitter amplifier. And we know that in this structure, if the transistor is not perfect, we have an early effect. And with the early effect, we end up with an output, the early effect resistance. And we know under these circumstances, the output resistance is going to be RC, and then in parallel with R0. And if you connect the output with a low resistance, in this manner, because the voltage supply here is considered as a ground, AC ground, and the output impedance is going to be, the output resistance is going to be RC in parallel with RO log and in parallel with RL. And the voltage gain, the input resistance here will be the intrinsic R pi of this transistor. The voltage gain is going to be AV and then minus GM times the total output resistance, which is this one here. Now, what happens if we add the tail resistance to the emitter of this transistor? So in this case, everything becomes changed. And for the output resistance, it's not going to be like this anymore. Instead, the middle term will be R and then 1 times GMRE, and the in parallel with output resistance. So in essence, R log here will be scaled upward by this amount, 1 plus GMRE. How about the input here? The input will be the same. It will be scaled up by GMRE. And similarly, in the formula of voltage gain, we have the output resistance change. And the transconductance, GM, will become scaled down by 1 divided by GMRE. So this is the basic of the Emitter Degenerated Amplifier. And another point is if you are going to look at the high frequency response, we need to look at the input resistance and output resistance. And I can tell you, in a transistor, there will be some parasitic capacitance attached, and the most dominant one is C mu. The second most dominant one is B pi. And there is another one here, and this one is only specific to the transistor, the bipolar transistor on a substrate. And in discrete element, this capacitance CCS doesn't exist. So we have another one connected to the collector here, and this one is CCS. And we are going to use these capacitances to analyze the high frequency performance. First, we have C mu, and C mu itself is equal to CJC. This is the junction capacitance between the collector and the emitter. When it is zero bias, when the transistor is under low bias. But what happens when it is under bias? Then the formula here has to be changed. It is most likely, it's like this. VCB divided by VJC. VJC is the junction voltage at zero bias. Normally it is about 0.7 volts. And you also need to it's like this. So where MJC is approximately 0.5. Now our C pi. C pi is a capacitor connected to the emitter. It is a very small island between the anode. So C pi is going to be 2 CJE times GM TF itself is the forward transit time, and CJE is the junction capacitance between the emitter and the base. And fortunately, CJC, DJE, TF, and MJC are all 5 parameters. And to analyze the high frequency performance, we need these parameters. We also need to apply some techniques to make sure the capacitors are connected to a node, from a node to a ground. I like this one here. Unfortunately, C mu have no direct pathway connected to the ground. One of the terminals is connected to the C terminals. of the transistor. The other is connected to the base. And in a similar manner, the capacitance C pi has a connection, has a lead connected uh, to the base, and another one is to the collector. And this is the intrinsic capacitance. You cannot remove it. Same goes for this one and this one. They are all intrinsic. There's no way you can remove it. Now, what we can do is we use some circuit techniques to break down this C mu so that it becomes another capacitance, like what is here. And this is so-called something. And according to Muller effect, this capacitance, as a result of C mu, is going to be C mu 1 minus AV, where AV is the voltage gain here. And according to this formula, you can quickly write down, you can substitute AV with this amount, CGM and then RC, R naught, 1 plus GM, RE, and do not forget the low resistance, RL. And how about C pi? C pi is the same. It can not the same, but it can be transformed in a similar manner. It can become this kind of capacitance, and the capacitance here is going to be C pi 1 over 1 plus GM RE. You can use the Muller effect, Muller theorem to derive it. So right now, almost everything is done. But we have two capacitors connected in parallel. Would it be fair if we just merge them into one? The answer is yes. This one plus C pi 1 over and we can eliminate this capacitor. And on the other hand, because of this capacitor, you can use Muller effect to convert the equivalent for this lead here. And according to the Muller effect, this capacitance is C mu and then 1 minus, and AV is the same formula here. And again, you can just rewrite the formula. And for the time being, these are the formula that we can use later. And we can say C mu is equal to 1 plus, like what we have here, 1 minus GMRE, and then divided by, we just flip it, GM, and then the chunks of output resistance. And to save space, I can just write R out. So we don't need to struggle with space here. Yeah, because we have RR, the expression RR here. And same in here, right? We don't need to write so much. We just say RR. So we make our life much easier. Now you have two capacitors connected in parallel. This means they can be merged together as a parallel combination. So CCS. And this capacitor, let's see, let's call this C out. So C out is this one here. And let's say this one is C in. And now with this much information, we can work out the high frequency effect. And now this capacitor has been transformed, so it should be eliminated. It should be erased. The pole can be directly determined. Under the mirror effect, every point in the circuit, every node in the circuit can potentially produce a pole, depending on the equivalent resistance and capacitance pathway connected to the ground. And at the input node, we have one capacitor, CE, connected to the ground. And we have a chunk of resistance. This one here, which is the R pi, RE here. So under these circumstances, we have one pole. Poles mean the quantum frequency. We start with this one, out. This means the pole connected to the C out. It is 1 divided by tau pi and the resistance. The resistance will be the total output resistance, which is this one here. And the capacitance, which is C out, which is this one here. Now we will write down the full formula. GMRO. With a program, with a MATLAB software, you can determine this expression very easily. Now, how about here? The input, similarly, we can create another pole. We can work out another pole where at the input. And this one is the pole due to the capacitance, C in. And according to here, it is 2 pi C in, R in, right, which is this one here. And the capacitance in the input, which is C in. I'm not going to write down the full formula. Now, the high frequency response has been done. And if you ask me to plot this out, I can just tell you if you want to plot out the frequency response in mode report, it will be like this. And will have the vertical axis in the form of voltage gain, V out over V in, and it has to be measured in dB. And the frequency response will appear like this. And this is so-called mid-band gain. And the mid-band gain is given by AV. AV. AV is equal to minus GMRE, and then times the total output resistance. The total output resistance, as I have already emphasized, it is equal to RO 1 plus GMRE, and then in parallel with RC and in parallel with RL. You don't have to lock in here. You have to be mindful. RC is RL. So this is really, and make sure you understand that it has to be measured in dB. Now, most likely, the first pole will appear at the right at the corner, and this one is most likely FP in. The second pole will most likely FPO. The slope here is 0. The slope here will be minus 20 dB per decade. The slope here will be minus 40 dB per decade. So this is the way how we plot the body part. Now, the high frequency response has been worked out using our technique. The problem is we are now dealing with a schematic of the Cascode of the Emitter Degenerated common emitter amplifier. The base is unbiased. It's not going to work. In order to make it work, you have to bias it. One of the ways to bias the circuit is to use the voltage divider technique. So in this case, we have to give some voltage, DC voltage, to the base so that it works. Otherwise, without any biasing, the circuit is not going to work. So R1 and R2. So this is the only way that can make it work. And now, with this kind of input, with this kind of biasing network, the input cannot be fed directly to the base. Instead, the input will indirectly fed. And most likely, it will be through another coupling capacitor, say C1 here. And this C1 will be much, much larger than C in and C out. The wire itself also carries some resistance, RS. And this is going to be VS, the source voltage. And with this in mind, we also need to pay attention to the output. The output, if you extract the output in this way, the output will be biased to a very high voltage. It will be leveled up by a DC voltage. So to filter off all the DC, you need another coupling capacitor here. And this is the standard way of using the emitter degenerated common emitter amplifier. So now you have connected the output in this way, and at low frequency, the output will be differently structured. Yeah. Okay. Uh, let's say, right, we are now beginning to understand the circuit now. We are going to look after the low frequency response, which is this part here. And we need to work out the poles associated with the C1 and C2. And C1 and C2 are high capacitances. And because of the high capacitances, it will produce low frequency response. But how about the intrinsic capacitance, C mu and C pi here? It's not going to affect the low frequency because the capacitance intrinsic to the transistor is indeed too small. You have a C mu here, but C mu is just mini. C mu is in the order of a picofarad. So at low frequency, it's just non-existent. C pi the same, a couple of femtofarads. So it's not going to affect the low frequency response like what we have here. So in other words, you can just safely eliminate this capacitance when dealing with the low frequency response here. So we take it out and we take this out. And we take this out. So we have only C in and C out left over at the end. Now, we need to work out C1 and C. We need to work out the poles associated with C1 and C2. Depending on the nature of the network. Right now, it is a series pitch. In this case, it is a capacitance C1 connected with a resistance RS. And when we are dealing with frequency analysis, all the independent voltages will be sorted to ground. So this one is essentially grounded. Okay? We see one, and how about the capacitance here? The capacitance here has one here, R1, and one here, R2, and the other one here is the input impedance. And this input impedance is R pi times 1 plus GMRE. We have already worked this out before. So this one grounded, and this one grounded, and this one grounded. So in action, right? The left side of the of the capacitors is connected to CS. The right side of the capacitor C1 is connected to this capacitor. To calculate the pole associated with C1, we need to do this. Yeah, CP and then C1 here. This is going to be 1. Let's dump this out. Divided by 2 pi. And what else? ROS. C1 first, and then ROS, then pass the resistance on the right side. This one, and this one, they are all in parallel. So this is the low frequency pole. And how about the one associated with the output here? Now I don't think you need this part, right? This circuit. And now we have C2 here. The right side of C2 is connected to RL. The left side is complicated. We have 2 resistance. One is RC, the other is R log, and then times some resistance. Right? And we know this, right, from the linear level theory. This one is going to be RO, RO times 1 plus GMRE. And normally we use this way to represent this capacitor. You use an arrow pointing to this side to represent the capacitance under this wire connection. So now, right, we can just work this out. Right? CPC2 is equal to 1, and then chunks of expression. I hope you can read it very carefully. 2 pi and then C2, which is the output capacitance here, and then the resistance. Now let's take a look, right? It is a series connection to this one, right? RL plus, and then the V in parallel. RC log the 2, yeah, and then parallel with RO log 1 plus GM RE, yeah. So this is not output resistance. It is a combination of this and that connected in parallel. So so this is the second pole, and we don't know the position of this pole in the frequency axis. The horizontal axis of this body part is frequency, and the unit is hertz. And perhaps it can be like this. So this one become minus 20 dB, and this one become 20 dB per decade. And this one become 40 dB per decade. And you have two pole here, one is the corner here. And as I said to you, we don't know which one first, right? Uh, chance is that this one become FPC1, this one become FPC2. We don't know. P something, right? C something. We don't know which one is which, okay? Uh, right now, I think I have already given you most of the information here. One thing I need to remind you, the unit dB. Right now you have an AV. We know AV is the voltage gain given by this formula here. And if you want to convert AV into dB, you need to do this. And 20, and then log 10. We need to convert it into power. And then V out over VE, just like this. Remember, right, it is a magnitude. So this is so-called the mid-band frequency. Okay, I hope it is clear enough to you. And if you have any question, please leave your question to the comments box, and I will try to explain to you. I will try to answer your question later. Thank you very much. Bye-bye.